Let's talk about building a solid network. We all know redundancy is king, right? Having multiple paths for your data seems like the ultimate safety net. But what if I told you that very safety net, if you're not careful, could actually be the thing that brings your entire network crashing down?
And you'd be absolutely right. In theory, it's perfect. One cable gets unplugged, a switch goes down, no problem. The traffic just zips over to the backup path. It's the whole foundation of a network that can take a punch and keep on running. You never, ever want a single point of failure.
But here's the catch. Network data, especially at the switch level, isn't meant to go in circles. When you just plug in extra cables between switches to create those backup paths without some kind of traffic cop, you've just created a loop. And trust me, that loop is a ticking time bomb.
And that bomb? It's called a broadcast storm. It's this insane, unstoppable flood of data that just keeps duplicating itself, overwhelming your switches, maxing out their processors, and grinding everything to a halt. So, how do we get the redundancy we need without the risk?
So here's our game plan for this explainer. First, we're going to stare right into that network loop nightmare. Then we'll introduce the hero of our story, Spanning Tree Protocol. After that, we'll meet its bigger, faster family members, show you how to actually put it to work, and wrap it all up with the one big takeaway for building a truly resilient network.
All right, let's really get into the weeds of what's happening when a network loop forms. It all comes down to the super basic, fundamental way that your network switches think and operate at what we call layer 2.
You know, it all starts so innocently. A switch gets a broadcast frame, and it just does its job. It floods that frame out of every single one of its ports, trying to find the right destination. But in a loop, that same frame almost instantly comes whipping back into the switch from another direction. The switch, not knowing any better, thinks, oh, a new frame, and forwards it again and again. It's an endless, vicious cycle. And here's the kicker. Unlike traffic on the internet that has a timed alive counter that eventually kills it off, these frames have no off switch. They will loop forever, multiplying like crazy until they've choked out everything else on the network.
A single, simple loop can absolutely wreck an entire company's network. This isn't just theory. It is a real-world disaster that happens all the time. Luckily, the folks who invented this stuff way back in the 80s were brilliant. They saw this problem coming and created a beautiful, elegant solution, the Spanning Tree Protocol, or STP.
Now, here's the most important thing to get about STP. It doesn't get rid of your redundant cables. It manages them. Its one and only job is to look at the whole network, map out all the possible paths, and then logically block any link that could create a loop. So you're left with just one clean, active path from A to B. But, and this is the magic part, it keeps those blocked links in its back pocket, ready to be activated in a split second if that main path ever fails.
So how does it pull this off? Well, all the switches running STP are constantly chatting with each other. They use these special little messages called Bridge Protocol Data Units, or BPDUs. The easiest way to think of a BPDU is like a switch's resume. It says, hey, I'm switch X, this is my ID, and here's how good I think my connection is to the center of the network.
What happens next is basically an election. All the switches send out their BPDUs, the resumes. They all look at each other's bridge IDs, and in a sort of backwards election, the switch with the lowest ID number wins. That winner gets crowned the root bridge. It becomes the North Star, the single point of reference that the entire loop-free network is built around. Okay, so STP was born in the 1980s. And let's be real, networks have gotten just a little bit faster since then, right? So the protocol had to evolve. It had to get faster, smarter, and way more efficient. Let's take a look at how it grew up. The biggest jump, by far, was from the original classic STP to what we call rapid STP. See, the old version used these really slow timers. If a link went down, it could take almost a full minute, up to 50 seconds, to bring a backup link online. 50 seconds! In today's world, that's a catastrophic outage. Rapid STP, or RSTP, threw those timers out the window and replaced them with a lightning-fast handshake process. That cut the recovery time down to less than 2 seconds, a total game changer. But it didn't stop there. The next brilliant idea was, hey, instead of one spanning tree for the whole network, what if we made a separate one for each of our virtual LANs, our VLANs? And this opened the door to an amazing feature, load balancing. Now you can tell your network, okay, use this link as the main path for all our user data, but use that other link as the main path for our phone system. All of a sudden, that expensive backup link isn't just sitting there doing nothing, it's actively carrying traffic. And this table just lays it all out perfectly.
Look, for any modern network, you're looking at the fast options. If you're in a mixed vendor environment, RSTP is your best friend. If you're running mostly Cisco gear and you want that awesome load balancing, RVPST Plus is the way to go. And for the huge enterprise networks with hundreds and hundreds of VLANs, MSTP gives you all the same benefits, but is way easier on your switch's processor.
Okay, so we get the why and the what. Now for the fun part, the how. You don't want to just turn STP on and hope for the best. You need to be deliberate. You need a plan. Let's walk through a super simple 3-phase strategy.
First, you audit and plan. You got to know what you're working with, right? So you map out all your switches, all your links, and all your VLANs. Second, you configure your root bridges. This is huge. Don't let that election happen by chance. You want to tell your most powerful core switches to be the root. And finally, you lock down your edge switches, the ones where all the computers and phones and printers actually plug in.
Choosing your root bridge is actually really easy. You just go into your main switch and set its priority value to be crazy low. Remember, lowest number wins the election. So with this command, we're basically shouting, hey everyone, for VLANs 1 through 10, this switch is the boss. Then you'd go to your backup core switch and give it a slightly higher priority, making it the vice president, ready to take over if needed.
And this step is just as important. For any port where a regular device, like a PC, connects, you enable these 2 features. Port fast is for speed. It lets the port come online instantly, without waiting for STP to figure things out. And BPDU guard is your security guard. It puts a rule on that port that says no other switch is allowed. If it ever sees a BPDU message from another switch, it knows some user has plugged in something they shouldn't have, and it instantly shuts the port down to protect the network.
So, we've gone through all the theory and the configuration commands. What's the big picture? Why does taking the time to master STP really elevate your network to a whole new level of professional reliability?
Here's the bottom line. STP is your silent guardian. It's the one thing that prevents those network-killing broadcast storms. The modern versions let you turn your expensive, idle backup links into active, useful pathways. A good STP plan is what separates a fragile network from a resilient one. And just remember this, no user will ever call you to say, hey, thanks for correctly configuring spanning tree, but they will absolutely scream bloody murder the second it's missing and a loop takes them offline. It's the invisible protocol that delivers very, very visible stability.
So I'll leave you with this to think about. You've probably spent good money on redundant switches and extra cables to guarantee uptime. But have you spent the time to make sure those paths are actually smart? Because redundancy without intelligence isn't resilience. It's just an accident waiting to happen. Thanks for tuning in.